Hi guys, this is A2 Chemistry, Transition Elements, and we are looking at color of transition metal complexes. Question 1. Explain why complexes of transition elements are often colored. So, binding of ligands causes an energy gap to be created between the d orbitals. An electron from the lower set absorbs a particular wavelength of visible light and transitions to the higher set. The color complementary to the wavelength absorbed is observed. So we need to remember that when ligands come and bind to the transition metal ion, the 5d orbitals that were of equal energy are now split into two sets, and electrons in the lower set absorb visible light and move to the higher set. This visible light that is absorbed has a wavelength lying in the visible region of the electromagnetic spectrum, and the remaining light that passes through the transition metal ion solution has a complementary color to the one that has been absorbed, and that is the color that is observed. Question 2. Explain why transition element complexes are often colored. They are colored because an electron from the lower set of d orbitals absorb visible light and not visible entirely a particular wavelength, and transitions to the higher set, and this is the reason for color. The color of a complex of a given transition element often changes when when the ligands around it are changed. The energy gap between the two sets of d orbitals is created due to binding of ligands. If the type of ligand changes, it results in a change in the energy gap. And since the energy gap changes, so the wavelength of light absorbed also changes. So the wavelength of light absorbed also changes. Heating a solution containing potassium ethane diode, iron 2 ethane diode, and hydrogen peroxide produces the light green complex K3FeC2O4 thrice, which contains the ion FeC2O4 thrice 3 negative. The structure of the ethane diode ion is as follows. So it has got a 2 negative charge. Calculate the oxidation number of carbon in this ion. So it is C2O4 2 minus. So the oxidation number can be calculated by the algebraic equation 2x minus 8 equals minus 2. And then this would become 2x equals plus 6. So x would be equal to plus 3. So the answer here is plus 3. Calculate the oxidation number of iron in FeC2O4 3 negative. So here we would have overall charge of 3 negative. Iron is X. C2O4 is negative 2. So negative 2 into 3 is minus 6. X minus 6 is equal to minus 3. And then we would end up with X equals minus 3 plus 6, which is equal to plus 3. Therefore, the charge on the iron ion in the complex is also plus 3. The iron atom in FeC2O4 thrice 3 negative ion is surrounded octahedrally by 6 oxygen atoms. Complete the following display formula of this ion. So we have 3 oxygens already present. So 4, 5, and 6. So this completes the presence of 6 oxygen atoms. And now, in order to complete the ion, we have this structure. This would be C double bond O, and this would also be C double bond O. For the next one, we would have C double bond O and C double bond O here. And for the third one, we would place C double bond O and C double bond O here, thus completing the structure of the given complex. Next, in sunlight, the complex decomposes into potassium ethane diode, iron 2 ethane diode, and carbon dioxide. Use oxidation numbers to help you balance the following equations for this decomposition. Okay, just by looking at the reactants and products, there is something we need to look at very carefully. There are 3 potassiums here and 2 here. This cannot be balanced at all. So what we need to do is we need to multiply this by 3 and this by 2 in order to balance the potassium. So now that the potassiums have been balanced, now we have 2 moles of iron. So we place 2 over here, and now, in order to balance the carbon and oxygen, let's calculate the carbon and oxygen on either side. So on the left, we've got 2 3s are 6, 6 carbon, and 4 3s are 12 oxygen. On the right, so far, we've got 3 2s are 6 carbon, and this would be multiplied by 2 because we've placed 2 over here. I'm talking about the one on the left. So 12 becomes 24, 6 becomes 12. So balancing on the right, 3 twos are 6, 4 threes are 12 over here. Then we've got 2 twos are 4 carbon and 4 twos are 8 oxygen here. And the remaining carbon is 6 and 4, 10, 2 carbon. And we are left with oxygen out of 24, 12 and 8 is 20. We're left with 4 oxygen. Therefore, we place 2 before carbon dioxide in order to balance this equation. Question 3. Carbon monoxide reacts with a ruthenium 2 chloride complex according to the equation given. Describe the type of reaction that is occurring here. So we've got 2 water and 4 chloride ligands on the left and 1 water, four chlorides on carbon monoxide as a ligand, and one water molecule has been removed. So, what is happening is one water molecule is being replaced by a carbon monoxide molecule. So, this is what is known as a ligand substitution reaction. During the reaction, the color of the solution changes from deep blue to green. Explain why. Explain the origin of color in transition element complexes and why different complexes often have different colors. So, presence of ligands split the d orbitals into two sets with an energy gap between them. An electron from the lower set absorbs a particular wavelength of visible light and transitions to the higher set. A complementary color to that absorbed is observed. And the other thing that is asked, why different complexes often have different colors. Different ligands create different sized energy gaps. So the wavelength absorbed is different. And because different wavelengths are absorbed, therefore the color observed will also be different. Question 4. Explain why transition element complexes are often colored, whereas compounds of S block elements such as calcium and sodium are not. So, the color of transition metal complexes is due to absorption of a particular wavelength of visible light by an electron in the lower set of d orbitals and its transition into the higher set. The color absorbed is complementary to the wavelength of color observed. So this is what happens in transition elements. The question also asks compounds of S block elements such as calcium and sodium are not. So we continue. S, or rather we start with this process does not happen in S block elements. So if S block elements do not have this process occurring, so they will not absorb visible light and will not have colored compounds formed. Question 5. Copper forms two series of compounds, one containing copper 2 ions and the other containing copper 1 ions. Complete the electronic structures of these ions. So, copper has an atomic number of 29, and they've mentioned square brackets AR, which means the electronic configuration of argon has been mentioned here, which goes up until 3p6. So, we continue the configuration with 3d10, or rather this is copper 2 plus ion, so this will be 3d9. 3d10 would be in copper 1, so 3d9, and copper 1 would have 3d10 as the outermost electronic configuration in the ion. Use these electronic structures to explain why copper 2 salts are usually colored. So the d orbitals are split into two sets with an energy gap between them. Electrons absorb a particular wavelength of visible light and is promoted the color observed is complementary to the light absorbed. So this is the reason for color in copper 2 salts. Copper 1 salts are usually white or colorless. Since the d orbitals are completely filled, there is no space for an electron to transition to. Therefore, copper positive ion salts are white or colorless. If the electron does not absorb visible light, a complementary color will not be observed. And if there is no complementary color, then that means that there is no transition of electrons. So the salts would be white in the solid state, and if soluble, colorless in the aqueous states. Question 6. On the diagrams below, show the outer electron arrangement of the atoms and ions indicated. Use the symbol up arrow and down arrow to represent a pair of electrons in an orbital. So iron has an atomic number of 26. So 4s will have 2 electrons present in it, and 3d will have 6 electrons present. So 1 in each of the 5d orbitals, and the sixth one would be the one pairing up in the first d orbital. For Fe2 plus, 2 electrons would be lost. So the 2 electrons lost are from the 4s orbital. So that means one electron in each of the d orbitals, but now the d orbitals are split into two groups, and we would have one electron pairing up in the first orbital in the lower set. For the third ion, we've got zinc 2 plus. Zinc has an atomic number of 30. When it loses two electrons, the 4s orbital becomes empty and the 3d orbital ends up with 10 electrons present. So all the 3d orbitals will fill up singly first, and then the electrons will pair up in each of the d orbitals, completing the electronic configuration of 3d10. Use the above diagrams to explain why Fe2 plus ions are colored, whereas Zn2 plus ions are colorless. So in Fe2 plus, electrons absorb visible light of a particular wavelength and are promoted to the higher set of d orbitals, and the color complementary to the wavelength absorbed is observed. In Zn2 plus, the d orbitals are completely filled, and this process cannot take place, leaving Zn2 plus salts white and colorless solutions for Zn2 plus soluble salts. So this transition from the lower set to the higher set cannot take place in zinc. So light in the visible region will not be absorbed. So color will not be observed.